So we near the end now. There is much more that could be said on almost any topic we have covered so far, but we have to draw the line some point. I do want to make some final comments here on a few matters that we've touched on before in some cases, but want to highlight them a little bit more. We'll also have a summary for week 8, of course, and I'll do a summary video for sort of the whole course, not everything in the course, but some of the key concepts, a roadmap through the course, our journey through the course, as it were. So I want to do 4 things here under final comments. First one is the role of crucial experiments. I believe along the way I mentioned the experiments of Walter Kaufmann, who was actually spelled with only one F. Many times you say it with 2 Fs, but Walter Kaufmann, German experimental physicist, and in the years after the discovery of the electron in the late 1890s, he and others were doing experiments figuring out what was known as the charge to mass ratio, E being the charge of the electron, M being its mass. And he especially focused on what happens if you shoot electrons at higher and higher speeds. And he shot them through various electric and magnetic fields, and because they had a charge, when they go through an electric field, there'd be a deflecting force, so they move in certain directions and certain distances. And then in a magnetic field as well, a moving charge would feel a force on it. And because the theories, the understanding at the time, said that charge did not vary with velocity, and still doesn't, but the idea was mass does because of Einstein's equation. And there were others who had similar ideas like this just from the experimental results. But one way to interpret, remember Einstein's energy equation here, gamma mc squared, is that if you look at this part, you can say that's what's sometimes called the relativistic mass. And it changes with velocity by the gamma factor here. Now, in more modern terms as it developed, usually we think of the mass just as the rest mass, and we don't think of the mass actually changing with velocity, but think of the energy changing with velocity. But you can also think about it in terms of just the mass increases with velocity. That's often, often hear that said about one of the results of the theory of relativity is that at higher and higher velocities, the mass of a particle actually increases. And so that's what Kaufmann was looking at here. He was saying, okay, the charge is going to be constant, is not going to change at higher velocities, but the mass will. And therefore, you could do various measurements. And out of these results, he had a series of experiments in 1902, so even before the miracle year of Einstein, even before the special theory of relativity, there were other people working in these areas, as we've mentioned before, but coming from very different directions than Einstein eventually did. 1902 he had some, and then in 1905 a more accurate series of experiments. And at the end of those experiments in 1905, he said this. His result was, the prevalent results decidedly speak against the correctness of Lorentz's assumption as well as Einstein. Lorentz, of course, had his own ideas and theories here that were similar to Einstein. Remember, that's why we call it the Lorentz transformation, or transformation equations. And basically, Kaufmann was saying, my results here are pretty definite, and they speak against sort of the Lorentz-Einstein way of looking at things. And interestingly enough, what happened is really nothing as far as Einstein was concerned. Max Planck actually looked at the data a little bit more, did his own reanalysis of the data, and said, well, it's not quite as definite as Kaufmann maybe makes it out to be, but seems to be getting pretty good data. Einstein himself, however, said this in 1907. You may remember I've mentioned a review article on the theory of relativity, and in that he analyzed some of Kaufmann's experimental results, gave those results. And Einstein basically said is that even though these results favored some of the alternative theories in the model of the electron they were trying to create at that time, he said that they were unlikely to be correct. The alternative theories were unlikely to be correct, even though the data seemed to fit them better, because they were less general than his theory was. They were more ad hoc and so on and so forth. So even though the data seemed to be against Einstein's theory of relativity, he said, nope, I'm going to stick with the theory. It wasn't actually until 1914 that things got cleared up and they were able to figure out that, yes, there were some subtle errors in the data here. So that's one so-called crucial experiment, because often we have this idea in science that you have something like somebody has a hypothesis, like Einstein did, then you make a prediction from that hypothesis, and then people do some experiments, and perhaps the prediction is refuted. So essentially what Calvin was saying is, I have refuted the work of Einstein and the related work of Lorentz as well. And then people reject the hypothesis and go with the experimental data and try to come up with something new. In many cases, that's not how it works at all. And part of it is that any given experiment is loaded with, sometimes the term is, I was going to say loaded with theory, but is theory-laden. Because if you think about it, any physics experiment, modern physics experiment certainly, has very complicated equipment. You need theories about how the equipment is actually working, how whatever you're observing is actually behaving within that equipment, and so on and so forth. So there are all kinds of ways, subtle ways, where experimental results can be wrong besides just mismeasuring something like that. And so it's just something to remember that science is never quite as simple as we make it out to be. And in fact, you may remember back in week 1, one of Einstein's quotes that we highlighted, he said, "Science is something coming into being as a goal is just as subjectively psychologically conditioned as are all other human endeavors." Not speaking specifically to a point like this, but it's a good reminder that there's a lot of leeway in things like this, and things are often not quite as cut and dried as they might seem. So, role of a seemingly crucial experiment, yet in the end is experiment that was shown to be wrong, and Einstein and Lorentz in this case were correct. Another example of a crucial experiment we've mentioned before would be the 1919 eclipse expedition results. This was to test the idea that light actually bent, starlight going around the sun. So again, the idea is something like this. If this is the sun here, here's Earth here. We'll say, okay, here's Earth. This is the sun, obviously not in the scale there. And you have some stars over here, okay? And when the sun's not there, okay, so when the Earth is over here, we can observe that star, which of course is going to be way out there. And it's in a certain position. But when the sun is between the Earth and the star, if Einstein is correct, then the gravitational field of the sun, as we argued, that light will actually be bent. And so the starlight, instead of just going in a straight line like this, will actually take more of a curved path to the Earth. And so what that means is that when the sun isn't there, so another time when they measure the exact position of the star, it will actually, if you think about it this way, it looks like on Earth that the star is right here. So when the star's light is bent by the gravitational field of the sun, it seems to shift position, its apparent position, whereas another time when the sun wasn't there, it would be measured in its correct position. But because it's bent like this, we see it in a slight shift of position. Now, it's a very subtle shift here, and very difficult to measure. And of course, as we mentioned, to measure this, you need a total eclipse of the sun, because otherwise the sun's light just washes out the starlight behind it. And so that's what they did in the 1919 eclipse expedition. The British sent a team to South America and also the west coast of Africa. And here again, you have to appreciate the difficulties of measuring something like this. It wasn't like, let's just take the photographs with our equipment and then it'll be very clear. But very subtle things, just shifts in the tripod a telescope could be set up on, differences in temperature that would affect the telescope just slightly, could cause shifts in just the image of the star that would wash out the actual effect that they were trying to see. And so once they even had the data, assuming the data was pretty good, and even that, sometimes you had clouds, of course, during the eclipse. You had trouble getting good star images. Sometimes they're a little blurry, and so on and so forth. And then you have to actually analyze the data and decide, is that data point good? Do we trust that data point? Or maybe that's really skewed in some way. Maybe there was a systematic error in that image, and so on and so forth again. So even though the eclipse expedition came back and essentially said in a very famous announcement at the Royal Society in London that Einstein was right. There was sort of a lot of human factor behind that. And if you look really closely at the data, it wasn't quite as unequivocal as it might seem. So again, here's a case of something that was taken as a crucial experiment in favor of Einstein's theory, and people basically accepted it because in the end, actually, it did turn out to be correct. Another example of a crucial experiment that people did not accept, and again, at least Einstein did not accept, and Einstein was right in that case. Other times, though, Einstein himself was wrong about things like this. So just have to realize that it's a much more complicated situation than often is presented in sort of the textbook cases of these things. And the general theory of relativity predicted other things besides the bending of light. It predicted or demonstrated that certain anomalies in the planetary orbit of Mercury could be accounted for by the general theory of relativity and weren't accounted for by Newtonian theory. So there are other things going for it as well. But even when Einstein won the Nobel Prize, the 1921 Nobel Prize, awarded in 1922, as I mentioned, it was not given for any aspect of relativity because it was still fairly controversial at that point, and many people were not sure whether it really was a good and correct theory or not. So just a few comments on the role of crucial experiments there. Now let's do number 2, the nature of genius. Books and books, of course, have been written on this. Scientists themselves tend to shy away from terms like this. Most physicists, of course, are very, very smart, and yet they do recognize sort of hierarchies. But it's usually, they can say, well, that person over there is definitely smarter than I am. I could imagine being as smart as they were. But sometimes there's just this qualitative difference. It's, in modern physics terms, a quantum leap above what everybody else seems to be. And there seem to be a few scientists, a few physicists who fit in that category. What are their characteristics? Just their originality, their creativity, their imagination. And you see all of that, of course, in Einstein's work. Just their thought processes almost seem to be such that you can't imagine how they came up with an answer, what's going on inside their heads. And Einstein was like that at certain points as well. Just his whole goal, his vision of thinking God's thoughts after him, in a sense. And yet this idea of a genius, almost like a magician-type genius, where again you see these things, they come up with these ideas, and you just can't imagine where they came from. Einstein himself shied away from that. And interesting enough, you can think of Einstein sort of, even though in a real way he was a revolutionary, he was at the beginning of the quantum revolution, as we mentioned before. He clearly, the development of the theory of relativity was revolutionary, both the special theory and the general theory. And yet, in a sense, you could say he was a conservative revolutionary in some ways, because he sort of had one foot in each camp. He went back to the classical theories. Remember how he started off with the special theory of relativity? He was very concerned about some asymmetries in Maxwell's classical theory of electromagnetism. That's what bothered him. And so he wanted to go back and fix some of those things, be true to the older theory, and out of that, though, came a real revolution. And he also was conservative in the sense that even though he'd started at the beginning with some of the ideas of the quantum revolution, as we mentioned before, he rebelled against it or went in a different direction later on in his career. So a conservative revolutionary, maybe a revolutionary conservative, if you want to think about it like that, both with one foot in the classical realm of physics and another foot in the more modern realm of physics. And other people put it like a reverential rebel. Walter Isaacson has a very good biography of Einstein. If you're interested in reading more about all of his life and work, that's a good one to pick up. Now, I will be giving you a list of books here in one of the handouts, so you'll have that among those listed. So, the nature of genius is hard to pin down sometimes, but certainly some of the key traits we've mentioned: originality, creativity. But there's also a single-minded passion that is involved from an early age. You see this, and Einstein certainly had it, to again sort of think God's thoughts after him, to figure out what the world was made of and how it worked. And because he had that passion, that drive, it enabled him to, or impelled him to put in a lot of time thinking about it. You may have heard of something called the 10,000-hour rule. When they actually study geniuses and exceptional individuals, they wonder, how did they, especially young people, how did they get so good at such an early age? They found that in many cases that they certainly had, and the third factor here we'll say is talent. They certainly have talent in areas, but a lot of people have talent and don't develop as much. But it's a combination of this passion that drives them to invest the time that, combined with the talent, then takes them to higher levels than many people reach. So a number of different factors that go into the nature of genius, as it were. Okay, so just a few words on the nature of genius. And let me just say one other thing. I think I mentioned this before, but the common story that Einstein failed math, wasn't good at math, and so on and so forth. He was very good at math. He taught himself calculus early teenage years, 13 years old, 14 years old, something like that. Later on in his life, he lamented that he wasn't as good at math as he needed to be, especially for the general theory of relativity. So he leaned on certain mathematicians. In fact, his friend Marcel Grossman from his student days, who became a professor of mathematics, helped him out. And so that's why he sometimes would say, a little girl once wrote a letter to him lamenting her struggles in math, and he essentially wrote back and said, if you think you have problems, I have even more problems with math than you do. So that may be how those stories get started. But he was very, very good in science and math from an early age. Okay, number 3, relativity versus relativism. A common misconception among many people, they equate the theory of relativity with the philosophical concept of relativism. That sometimes you hear, the theory of relativity, Einstein proved that everything is relative. And this is really an ironic misunderstanding, because as we talked about, in a certain sense, the theory of relativity is a misnomer. It could very easily be called the theory of invariance, because it's built on the idea that certain quantities are invariant. And the classic example is the speed of light. It's the same for all observers, no matter what reference frame you're in. And so that's clearly the opposite of the philosophical theory of relativism. But really, there's no connection at all between Einstein's theory of relativity, special theory or general theory, and the idea of relativism, even though they often get conflated, and that sometimes impels people to rail against Einstein and the theory of relativity because of that. So relativity versus relativism. Number 4. Last one for our final comments. Besides, again, we'll do some summary comments in another video. And this is a question: Is this all really real? When we talk about things like time dilation, do moving clocks really run slow? How do they move slow? Do moving objects like sticks, does their length really contract? Do they really get shorter? Or do they just appear to do that? And sometimes you even see physicists take that tack. There's still some debate about this, but I would say the best answer to this is yes. If the measurement of time and length and things like that has any meaning at all, then yes, these are really real effects. And of course, we can see them in the experimental results. We talked about the case of the muon coming down from being created by cosmic rays in the upper atmosphere and then getting down to the surface of the Earth. You can't explain how they get down here, given such a short lifetime, without the special theory of relativity. Or the GPS navigational system. you can't explain how that works. You can't even design the system without using the special theory of relativity and the general theory of relativity there. Particle accelerators as well. High-energy particle accelerators, like the one in CERN, the French-Swiss border is where it is actually. You can't design those things and get them to actually work without the special theory of relativity. So, yes, they are really real effects. Again, the theory applies to everyday experience, but because our speeds are so low, our common everyday speeds are so low, we don't observe the effects of relativity at all. And also, sometimes you think, well, relativity and quantum mechanics, they're separate from each other, and quantum mechanics really is the more modern theory and has a wider coverage of things. Actually, in quantum mechanics, relativity is built into it. It was developed in late 1920s, early 1930s, was put into a relativistic form. And so all the modern theories of physics that deal with particle physics and things like that have relativity built into them. And therefore, it's possible that we could come up with an experimental result, or really probably a series of experimental results, that called into question whether relativity was true, but we haven't so far. Everything has been consistent. And even if we did find something, it would probably be a very small type of correction. So, yes, it is really real. And going back to one of the original quotes we started off with in terms of the course, that the special theory of relativity, in Einstein's words, is part of the marvelous structure of reality.